is the Avro Arrow, Canada's entry into the supersonic era. Within the short span of 4 years, the Arrow was brought from initial design to the start of the development flight program. So vast was this project that during the next 20 minutes, we can do no more than give a series of impressions of the planning and hard work that was required. Early in the design stage, it was apparent that newer fabrication techniques would be needed. Because earlier methods of manufacturing portions of the aircraft skin from sheet metal would not meet design demands, an electronically controlled skin mill was installed to machine skins and structural components from solid metal billets. This 15,000-ton press was also installed by Avro to form heavy-gauge sheet metal parts with the accuracy that the Arrow required. Again and again, in the planning of the Arrow, the development of new manufacturing techniques was made by Avro to meet the exacting requirements of modern aircraft design. This meant the procurement and installation of new equipment with which these new techniques could be effected. In design and manufacturing, new and unexplored areas were being opened up. But this was far from being a purely academic investigation. The whole project was proceeding to a tightly integrated schedule, and it was a complex operation demanding a very precise analysis of manpower, machine, and facility capacities. From the master schedule, detailed programs for manufacture and assembly were prepared, and a smooth, pre-planned release of manpower from other programs to the expanding Arrow production line was effected. The success of this careful planning may be judged by the fact that the first Arrow took 20% less man-hours than projects of similar size and complexity produced elsewhere in North America. There is, of course, much more to designing and building than we have seen so far. It wasn't quite that easy. To see a little more of the work involved, let's go back to the beginning of the story of the Arrow. Avro's initial proposal for the Arrow was completed for submission to the Canadian government in 1953. Design specifications were based on requirements for Royal Canadian Air Force fighters of the future. Following government authorization of a design study, various carefully handcrafted scale models representative of the aircraft design were prepared for the wind tunnel development program. Within a short period of authorization, wind tunnel tests were being run. Models were tested at low and high speeds, and spin recovery tests were carried out. As a practical check of flutter and vibration calculations, a scale model was made and tested because existing theory did not adequately cover problems introduced by the low aspect ratio and complex structure of the Arrow. Records of all tests were analyzed and fed back to the design team. Of course, there is nothing as good as a full-scale model to check installation clearances and general accessibility. A wooden mock-up was built for this purpose and was also used for early RCAF evaluation. The dummy engine used with the mock-up to check installation and removal techniques is a full-scale model of the Pratt & Whitney J75 engine used in the first Arrow aircraft. The later more powerful Orenda Iroquois engine is scheduled for installation in later Avro aircraft. It has already been flight tested in a B-47 on loan from the United States Air Force and specially modified for this purpose. Using the mock-up, RCAF specialists were able to assess servicing requirements and make suggestions for design changes. Close cooperation between the Air Force and Avro has been a notable feature of all stages of the Avro program. A similar metal mock-up was built by the Manufacturing Division to establish and to check manufacturing methods, assembly, and work sequences. This early wooden mock-up of the cockpit showed that the windscreen, as originally designed, would be subject to distracting reflections. Using the mock-up, it was possible to correct this condition and check the result before a single aircraft had been built. A program of structural and systems tests was begun at an early stage in the project. A large number of test rigs had to be specially designed and constructed for this work. Some of the rigs were of a relatively simple nature. Others, such as the fuel system test rig, were much more complex. It was used for investigations into fuel system functioning under simulated flight and ground conditions. The Avro is fitted with Martin Baker seats for ejection of the aircrew under emergency conditions. Records of tests conducted to analyze the operation of the escape system show its effectiveness. The Flying Control System test rig is a full-scale replica of the aircraft system from the cockpit controls to the control surfaces. It is possible to reproduce flight loading on the rig and to conduct simulated flight tests. The automatic flight control system and analog computers provide simulated flight response. A complete full-scale air conditioning and pressurization system was developed in this rig. The rig can be fed with heated high-pressure air to reproduce the full range of operating conditions met in flight. This rig simulates the complete aircraft electrical system. It is used to check out electrical components or wiring assemblies before installation in the aircraft. It is possible to show only a brief representative selection of the many structural and systems tests which were performed as part of the Avro project. The testing of systems in rigs, simulating flight and ground conditions, the testing of materials to ensure that they would meet design requirements. All this was carried out with one primary aim in mind. The first aircraft was not to be a handmade prototype. A comprehensive test program to prove all aspects of design was therefore necessary before starting tooling for production. This test program included the building and testing of a number of 1/8 scale free flight models to obtain drag and stability information. The models carried telemetering equipment to transmit signals to ground stations while the model was in free flight. Each model was attached to a Nike rocket booster. During each flight, the airborne transmitter sent a continuous stream of information on the flight characteristics of the model to the ground stations. Additional information was gathered by kinetheodolite cameras and by radar, which tracked each flight. All this data was recorded and analyzed to ensure that the aero design was proceeding on the right lines. As testing proved the validity of design, production tooling was started with the building of these master models. They are the basic forming tools for contour accuracy of skinned sections. Building a first aircraft using complete production tooling eliminates delay when quantity production is required. This new approach to aircraft production has proved most successful and is being widely adopted in the production of other high-performance aircraft. As the thousands of drawings of tested, proven design were released for manufacture, the tempo of production quickened. Supersonic aircraft are virtually flying pressure vessels, and as such, the complete aircraft structure is subject to wide variations of pressure. This fact greatly influenced the design of the structure. The effect of aerodynamic heating at supersonic speeds has also been an important factor in the design of the aircraft. Although the extent of this heating is not so great as to make it impossible to use aluminum alloys, new alloys were used where practical to improve the performance and safety of the aircraft. For example, the large surface area and relatively low loading of the fuselage allowed the advantageous use of magnesium alloys, particularly those with good high-temperature properties. Because of its proven reliability, the J-75 engine was a logical choice for installation in an untried aircraft. However, when the Orenda Iroquois is installed, the full potential of the aero will come much closer to realization. Across the country, hundreds of associate contractors and suppliers providing equipment for the aero were making their contribution to its success. Each had a specified job to perform, and each had a delivery deadline to meet. All these operations had to mesh with the master schedule, the key plan for the production of the aero. Inevitably, in a project of this magnitude, there were some snags. There were occasional delays, and sometimes adjustments had to be made to keep the whole project rolling smoothly. But the problems were solved. The difficulties were ironed out. And by the late summer of 1957, the first aircraft neared the end of the production line. From the production line, the first aero was taken to the flight test hangar. Preparation for flight included exhaustive testing of the aircraft systems and ground running of the engines. Following completion of these tests, the aircraft began its taxi trials with Avro's chief experimental pilot, Jan Zurakowski, at the controls. During a series of low and high-speed taxi runs, he was able to familiarize himself with the taxiing characteristics of the aero and to check the operation of the wheel brakes, the drag chute, and various related systems. Finally, on the morning of March 25th, 1958, the aero is ready for the air. At 14 points around the airfield, motion picture and still cameras are stationed to cover takeoff and landing. As Jan Zurakowski climbs into the cockpit, 10,000 Avro employees and RCAF observers watched tensely from the edge of the airfield. Ground telemetry units stand by to record data transmitted from the aircraft. CF-100 and Sabre chase planes take off for visual and photographic observation of the flight. And in the Avro Tower, recordings are made of all verbal communications.
Alla skador förklar för underklädd detection.
Fuel readings, please.
655.
Burn from Frank. Altitude, please.
Altitude 8,500 ASI now 230. Leg sits completely snug in the wing. And the left leg as well is completely snug in the wing. Controls are behaving quite nicely. I can see no oscillatory motions of any description in them. I'll start returning to the left and then I'll put the indicator down now. Okay, Jan, give me time. I want to photograph this. The elevator is about 3 degrees or 4 degrees up as far as I can see from here. Ailerons are nice and fresh. Controls here seem to be quite normal, Jan. No problem.
Wind is 40 to 50 degrees, 10 to 1530. So 201, Toronto Tower, clear to land, wheels down, lock 32. Telemetry, he's touchdown.
Wonderful parachute, Jan, fine.
One down to 27, cleared to company.
After watching its historic first flight, the huge crowd of Avro employees and Air Force personnel greeted the arrival of the Arrow at its flight base. Because the first Arrow was produced from such complete production tooling, additional Arrow aircraft are being produced without the delay which usually follows successful first flight of a new aircraft. The success of the design is due in large measure to the intensive testing which has formed a major part of the program so far. Testing on the ground is continuing step by step with testing in the air. This full-scale structural test rig simulates flight loads on a static test aircraft, making it possible to predict many of the actual effects encountered in flight. These static tests naturally assume great significance as ever greater demands are made of the aircraft in flight. On its third flight, the Arrow flew supersonically. On its seventh flight, it exceeded 1,000 miles an hour while climbing. This is still well within the maximum capability of the aircraft, which will be achieved during the development flight test program. With its advanced electronic system and guided missiles, this supersonic Sentinel is designed to guard the Arctic approaches to the Western Hemisphere. The success of the Avro Arrow marks a new chapter in the history of the Canadian aviation industry and a new contribution to Western defense.